Thanks, Chairman, for introducing me. So I will talk about some other aspect of the same story of topological states, which is on this topological field description. And it's my great pleasure to come to Israel for the first time. It's a wonderful country, very beautiful weather, everything here. And of course, from whom I learned a lot, and more details are in the second slide. And but last but not least, I would like to thank my parents and my wife for all their love, especially because they may be watching this on the video. So someone who didn't do this may have a problem. Yeah, so I list my collaborators, and most of them I will talk about works with them, and especially Xiao-Liang and also Taylor Hughes and Mason McAshley, who are the two junior people I collaborated a lot and benefit a lot from them. And I would clarify that this is not a complete list of my collaborators, only those who the works are related to this talk, and among the collaborators who are not listed here were our previous two speakers, Andre and Liang. I'm not sure if you remember, but actually I wrote papers together with both of you. So thank you. Thank you very much. And so we're not only competitors. So the very short outline of my talk is basically after a 10-second review of topological insulators, which is not needed. Then I will talk about topological field theory approach, and I will explain what is a topological field theory approach to topological insulators. And then I will talk about topological field theory approach to other topological states, including topological superconductors. And in the end, I will talk about some more interacting, strongly interacting states, which is about this gravitational response of chiral topological states. So these are just three examples of topological field theory approach to topological states. So I don't need to say anything about this slide. But it's important to show it because this is like the genesis for topological physics. Like everything starts here, quantum Hall state, and then we recently the developments is that this quantum Hall story that you have a gapped bulk and then you have this robust gapless state moving on the edge is generalized to these invariant systems in both 2D and 3D. Our two previous speakers made pioneering contributions to these, and we have these topological insulators now predicted and realized. Okay, so we have these states. We know they're Hamiltonian, and we know they have these surface states, and they are observed. So now let's ask let's ask some different question about these states. So we know we want to say that the topological states are some new states of matter. They are qualitatively distinct from the matter we know before. And then for that, what matters is you need some transport. You need some response properties, some properties that you can measure, and then you can tell that it's qualitatively different from before. Of course, nowadays you can make spectroscopy measurements and you can directly see these surface states, and then you know they are different. But it's a little different from like you directly measure something like transport or specific heat and these kind of many-body properties. So that's the point of view of this response theory. So basically, given a system, given a state, a chunk of material, then what the response theory means is you perturb the system by some external force and then watch its response and then look at what's the response. So you can use different external force to probe a material. If you hit the material, then you are probing it by some maybe van der Waals force, and then you can probe the response by phonons by your ear. So then you can also shed some light on it, and then the response will be observed by your eye. So these are just simple examples of response theory. When I'm talking, then you are looking at the slides, and you are doing a response theory of me and the slides. So another example. So okay. So now let's to understand what we want to do more specifically, what we want to do to understand the response of materials. Let's take the example of the quantum Hall. So because that's the topological state that we first understood, we understood the best. So in quantum Hall, we know the reason why this quantum Hall is discovered is you measure the Hall conductance, and it's given by this formula, and it's quantized. So you pick a direction, call it y, and then the current along the perpendicular direction is related to the electric field by a quantized coefficient. So in terms of a response theory, what that means, I mean, you can translate that into an equivalent statement, which says that the effective theory of the electromagnetic field in this system contains such a term, which is called the transimpedance term. So the two statements are equivalent in the sense that the transport equation is given by taking equation of motion of this action over this gauge field. Right. So for any action, you can take the equation of motion. So if you know this, you know that. These two are equivalent. So it's in that sense, this is the topological response theory that tells you I have a quantum Hall. But okay, but you get more than that. It's I mean, if you already have a system, you know it has a quantized Hall effect. You know this. Of course, you can derive this action. But actually, the action tells you more. If you look at the action itself, it actually tells you, without knowing any detail of the system, it tells you that this number is an integer. So it gives you a general reason why this number is quantized. I mean, of course, this actually is assuming you know the system has only one ground state. So, and the reason of that can be interpreted by Bob Laughlin in this Laughlin argument. So basically, when you can think of an annulus, so this is an annulus. It's actually 2D. I think I made I shouldn't make this 3-dimensional effect. So this is actually 2D. So you thread a flux into the annulus, and then you change the flux from 0 to 2 pi, and 2 pi means hc over E. And then what happened during this process is when you change the flux in time, you generate a circulating electric field. And because of the Hall conductance, you will generate a radial direction current given by these red arrows. Right, so now you have these red arrows, and then when you integrate this current in time, you will find that for a system with a constant Hall conductance, then the charge pumped from inside edge to the outside edge is independent from how you thread the flux, and is completely determined by the initial and final state. If the flux changed by 2 pi from the initial to final state, the charge you pumped is just Hall conductance times that. So that tells you Hall conductance must be quantized. Why? Because the charge pumped must be quantized. The charge, because the final state is actually the same system as the initial state. It has the same Hamiltonian, because 2 pi flux cannot be observed, right? So since you have the same Hamiltonian, the only thing you can do in the end is you take some electrons from inside to outside, and that number must be integer. So this is a picture that that can be translated into a more mathematical argument that tells you, if you just look at this action, the only thing you need to know is there is this U1 symmetry, and U1 symmetry is compact, so you can have this 2 pi flux equal to 0. Then you can prove this coefficient is quantized. So that's what we learned from this topological response theory, that you don't need to know any detail of the system. It already tells you what are the possibilities. So now let's try to summarize the procedure that you use to get a topological response theory, because then we want to apply that to the topological insulators and the other topological states. So basically, you have this. So I summarized it in this 2 steps. So if you want to get a topological response theory, the first thing to do is you pick what external field you use. Remember that picture. You can hit the material with different external fields, and then you are talking about different response. It may not be unique. You may probe the same system with different fields. But so you will see there are cases where when you pick this one, you get nothing. When you pick a different one, then you get a non-trivial response. Right? So you need to pick the field, and then once you pick the field, you can write down what are the possible response. It's not about the detailed calculation of the system. It's just writing down all the possible terms, like the Chen-Simons term in the example. Right? So you write down all the possible terms, and then you ask, is the coefficient of this term or any parameter in this term continuously tunable? Or in another word, it means what are the values can the parameters take? If it's continuous, then it's not so interesting. And the interesting case is it's discrete. It means there are discrete families of terms you can write down which cannot be tuned to each other. And that's the case where you have this topological matter, because it tells you have different matter which give you these different discrete parameters like the integer. So that's the general philosophy. And I put this here because I discussed this in a chapter I wrote in this book. Maybe this is not as well sold as Andre's book, but it's an alternative choice. So some book about the topological insulators. So you can find a review of this thing there. Okay, so now let's apply this procedure to topological insulators. So the first thing is you pick a field. And then, of course, if it's an insulator, there is charge conservation. The first thing you want to pick is like follow quantum Hall. You use the electromagnetic field. Okay, you use the electromagnetic field, and then it turns out that a key thing is you cannot just use the electromagnetic field as I think Liang has already mentioned. You need some symmetry breaking on the surface. And what we've shown in this paper was that when you have surface symmetry breaking, whatever way, but in the end you gap everything. As long as you gap everything, you can write down this effective theory, which looks like a FYGF term. This is another topological term that is available in 3+1 dimensions. So in this paper, we actually derived this in a macroscopic way. You start from a model, you can derive this. But from the topological field theory point of view, the important thing is that you can write down this term even if you don't know detail of this system, even if it's interacting. So you know that there is such a response term, and then I will discuss that this coefficient is quantized when you have time reversal symmetry. So instead of talking about how that's derived, let's assume there is already this term and then ask why the coefficient is quantized and what's the consequence. So basically, when you write this term in the free energy, it's just E dot B. And what does E dot B in the free energy mean? You just write down the corresponding response, and you know B squared, E squared gives you paramagnetic and dielectric response. And so similarly, when you have E dot B, it just tells you magnetic field generates charge polarization and electric field generates magnetization. Okay, so why is this special? I mean, yeah, magnetic field may generate charge polarization if your symmetry preserves. But what is special is that this coefficient theta is actually periodic. So before we talk about any time reversal symmetry, this is just for a general insulator. So the theta is periodic. Why? Because this integral, if you do this integral in any closed manifold, is actually quantized. Just based on assuming charge quantization, you can show that this integral is quantized. It's the same as like a flash quantization of magnetic field. So because of the quantization of that integral, the coefficient only makes sense when you have only makes sense modulo 2 pi. So this periodicity is essential when you introduce time reversal symmetry, because once you know that this is an angle, then when you have time reversal symmetry, you just simply check the symmetry, the transformation of this term. You see that this angle is odd in time reversal, and once the angle is odd in time reversal, you know there are two values which preserve time reversal symmetry, which is 0 and pi. If you don't show this theta is actually an angle, then there will be only one dot left if you have time reversal, right? It will be 0. So the non-trivial thing is that you actually can have a non-trivial theta, which is pi. So there is a material which doesn't break time reversal symmetry in the bulk, but if you break time reversal symmetry on the boundary, you're allowed to have, you must have a non-trivial magnetoelectric coefficient. And there is actually a very simple way to understand what is happening to this system, why I have this magnetoelectric coefficient. So the simple way is you can show that this is related to the surface Hall conductance. So in the bulk view, what happens when you have this term in the action is electric field generates magnetization. But we know magnetization means nothing but some confined current, right? So you can equivalently describe the magnetization, uniform magnetization, as some current flowing on the boundary in the direction that's perpendicular to the magnetization. And that, so because M is proportional to E, so this current is also proportional to E. So that's exactly a Hall conductance. So a surface Hall conductance is actually equivalent to this magnetoelectric coefficient. To be more precise, it's equivalent to the jump of magnetoelectric coefficient on the surface. And then, okay, so then we can actually gain intuitive understanding why there is this effect. That's because when you look at the surface state, you have heard from the previous talks that the surface state is this Dirac fermion, and actually the Dirac fermion has this locking between spin and momentum, spin and velocity. So it has only one spin for each momentum, but when you change momentum, the spin must be rotating following it. So consequently, when you break time reversal symmetry on the surface, say by a magnetization, no magnetic field, just some magnetization. And when you apply a magnetization on the surface perpendicularly, then the magnetization will lead to a precession of the spin in the in-plane direction, right? And then because the velocity is locked with spin, this will mean that the velocity is also keep turning on one direction. And that's exactly what happened when you have a Landau level in the quantum Hall case. Right? So this is an intuitive understanding that why you have a Zeeman field in the system, just split spin, but you will see this orbital motion and quantum Hall on the surface. So just because the momentum and spin are locked. And moreover, when you have a domain wall between two different types of time reversal symmetry breaking, left-handed and right-handed, then on the boundary you can create this edge state, which is the same as a quantum Hall edge state. But here, so in quantum Hall case, if you see this edge state is like between Hall conductance 0 and 1, two liquids, or maybe 1 and 2. And here it's between 1/2 and -1/2. So the key thing that distinguishes this three-dimensional topological insulator from any other material is it has this half quantum Hall conductance on the surface, which is impossible for any two-dimensional non-topological ordered state. And the interesting thing is that this actually has been observed in two materials already. So this is a mercury telluride, where you can make a thin film of three-dimensional mercury telluride, and then you can measure the Hall conductance, and of course you see Hall conductance of the top and bottom surface together, so you still see integers, but you can fit them, and then understand that actually what you see is two surface states, each give you half. And there is this more dramatic recent experiment, which is called this quantum anomalous Hall state. So we proposed this quantum anomalous Hall state in manganese doped mercury telluride, but the recent discovery is in a different material, this doped bismuth selenide, which was proposed by Shou Cheng's group later. The advantage of this material is you have real ferromagnetism. So you have this magnetic doped topological insulator, bismuth selenide, and then you really have this ferromagnetism of these magnetic impurities, and then what you see is that dramatically you have this quantum Hall plateaus without any external field, just by Zeeman fields, right? So that directly demonstrates this surface quantized Hall conductance. Okay, so just briefly I will mention other consequences of this theta term. So basically, you can, all the consequences are given by this modified Maxwell equations. You just have this magnetoelectric term in the Maxwell equation, which means your charge polarization has a contribution from magnetic field, and vice versa. So once you have this, you can measure them other than the surface Hall effect. You can measure them in electromagnetic response. So for example, there were two proposals we made before. One is this Faraday rotation, which is you shed in a linear polarizer light on the surface, and then you see this Faraday rotation. And this is different from Euro Faraday rotation, which keep going because the material breaks time reversal or immersion. Here, it just happens at the surface, and the bulk is time reversal immersion. And this rotation angle detects this theta. And then the other effect is if you put a charge near the surface, you will generate an image monopole instead of in addition to the image charge, and that's a consequence that that you have this magnetoelectric coefficient. You see a monopole-like magnetic field. Before I go on to the more general topological states, is there any question? Yeah.
So the giant magnetoresistance effect in the beginning of the 90s, the explanation was given based on scattering of the surface because copper and carbon. Would you speculate that maybe we're dealing with a topological effect?
Probably not.
Between, say, a good conductor and a strong ferromagnet.
But I thought that system is a conductor. Right? So here we only have conductance on the surface, and the bulk is insulating. And when you talk about this like a quantized Hall conductance on the surface, that only occurs when you make the surface also insulating. So I guess it's a little different. Okay. So what we also did in this work where we proposed this magnetoelectric effect was that you see that once you describe this system in this topological field theory way, then it's very easy to generalize because the starting point is like quantum Hall, and then quantum Hall can be easily generalized to all the even spatial dimensions, all the space-time dimensions. So you have these transimus terms in all these even spatial dimensions, and there is this second transimus term in the 4D, for example. And then the way we actually get this theta term is actually by some dimensional reduction, which means you first understand this, and then you wrap it around, you compactify one dimension, and then you get this. And actually, if you follow this procedure, you find that there is a periodic structure in this family of topological insulators. If you look at the trunk, which is this quantum Hall insulators, it seems there is a periodicity of 2. Every 2 dimensions, you have a quantum Hall. But if you look at the branches, which are these Z2 insulators, means there is only 2 classes, trivial or non-trivial, then actually there are actually different dimensions require different symmetry. So when you have time reversal symmetry, you have this topological insulator in 3D and 2D. If you don't have time reversal, then they don't exist. But if you look at this descendants of the quantum Hall state in 1D, then you actually need a different symmetry. If you still use time reversal, you don't get anything. It's just based on symmetry analysis of these terms. In 1D, you need this particle Hall symmetry. That's actually a superconductor. Okay, so so when you check these different symmetries of different dimensions, you find there is actually a periodicity of 8. So when you go to 8 dimensions, it's the same. When you go to 10 dimensions, it's the same as 2D. So then it turns out that there is an even more complete story, which was shown in this work first, where they analyzed all the 10 symmetry classes. So what I shown in the last tree was actually contains 5 of the 10 symmetry classes. So what they shown is actually you can do this classification in all the 10 symmetry classes, and it was pointed out by let's say Kitaev that there is actually a periodic structure. So that's the so-called topological periodic table. So instead of showing a periodic table, I'm showing this. Chinese and Koreans certainly know what that is. And it's something called Taiji. And so the reason why I show it here is because the number 2 and 8 appears very nicely in that. And so basically you have these 10 symmetry classes marked here. And then there are 2 classes which doesn't require anything like time reversal, any non-unitary symmetry, just charge conservation, and another unitary symmetry called chiral symmetry. There are these 2 classes. And then this periodic structure in symmetry and dimension. What that means is that for any dimension, you have this diagram, and then there is an integer. So there is an integer insulator here, which is like quantum Hall in 2D. And then there is another integer insulator, and then there's 2 Z2 insulators. And when you change dimension, you just rotate the whole diagram. So you just so now this family has a Z insulator. So you just change it to different dimensions, right? So you just turn this thing around, and then you get a classification of every dimension and every symmetry class. And I haven't explained what are these symbols. Andre showed them in his talk. So there are different symmetry classes, and in particular, this one is the topological insulator. So I'm showing 3D. So there is a Z2 classification, and if you rotate it to 2D, there is still Z2. Right? So this class, which has one less symmetry, this class is actually topological superconductor. And you see it has an integer classification rather than Z2. So now if I rotate it to 2D, it actually has a Z2 classification. Okay, so in the following, now I will talk about this case, because this is one case which was not in the tree, and we can't apply these techniques for topological insulators to it. We need some new topological field theory description. So, okay. So you have heard some talks both in the morning and afternoon. You have heard about this topological superconductor. So in very short sentence, what topological superconductor is basically like superconductors which has a full gap, and then the band structure of the Bogoliubov quantiparticle plays the role of the band insulator band structures of electrons. So you just replace the electron by Bogoliubov quantiparticle, and everything else is the same in the mean field level. And then the thing I'm particularly interested in, there is actually a topological superconductor proposed a long time ago by Reed and Green. And the thing I'm particularly interested in is this time reversal invariant topological superconductor in 3D. So what happened is there is this topological insulator with the surface Dirac cone protected by time reversal symmetry. And there is a cousin of it, which is a topological superconductor. That's actually helium-3b. So the surface state of it is a Majorana fermion, which has a protected degeneracy. So basically, it's like half of this with this image, particle hole image. So it only contains half of the degree of freedom. Okay, so but if you follow this analogy, naively you would expect that this topological superconductor is the same as the topological insulator case, which is classified by Z2, which means there is just no, there is a Dirac cone or no Majorana cone or no Majorana cone. But actually it's Z. So how do I understand that the classification is actually integer? I won't give a most general definition or most general classification, but I would like to explain this formula we have when we have where we have a view from the Fermi surface. So this is a paper we wrote in 2010, and so what happened is you can, because superconductor is essentially it's a Fermi surface phenomena. You don't need to involve the whole band structure. Right? In practice, pairing is always much weaker than other things. So you look at the Fermi surface, and then you look at pairing on the Fermi surface. So what happened is that the criteria of topological superconductor in this case is very simple. You just look at all the Fermi surfaces, and each Fermi surface is 2D. Right? Now I have 3 dimensions, so each Fermi surface is 2D. And if you look at this Berry phase curvature, which is like a gauge field living on the Fermi surface in the momentum space, then you can integrate over the Fermi surface. You define a flux, which is quantized, which tells you how many monopoles are enclosed in the Fermi surface, and they give you a number. So like in this case, there is 1 for the blue and -1 for the red, and then the criteria of topological superconductor is you want this Fermi surface with different Chen number to have opposite sign of pairing. You basically do a weighted sum of different Fermi surfaces of the sign of pairing and the Chen number. And if you have the same sign of pairing everywhere, this is guaranteed to be 0 for some no-go theorem. But if you have some alternating sign like what is shown here, you can get topological superconductivity. So why is this useful for the topological field theory description? Actually, this helps us to basically relate this topological superconductor to other topological states, which means you can first realize this normal state and then introduce this alternating pairing. Right? So you see that you need some Fermi surface with Chen numbers, and these are these Wilson metals that Andre also mentioned. So basically, if you look at these 2 Fermi surfaces, I don't care much about how they are connected. They are connected like the Rashba dispersion or something. The only thing you care is you have this Dirac cone with you have this well cone with a Chen number, and you have the other one with opposite Chen number. So and then you pair them with a different phase. So then there is a very natural way to realize it, maybe not very natural for experimentalists, but a very natural way to realize it conceptually, which is you put a 4+1 dimensional topological insulator. Remember this thing on the trunk of the tree. And then the surface state of it is guaranteed to be this Fermi surface, this well fermions which has Fermi surface with Chen number. So you have this 4 plus 1D material with 2 surfaces, and they have this Fermi surface on it. And then the only thing you need to do is you introduce superconductivity on the surface, just like what Charlie and what Liang and Charlie did for a 3D case. You introduce superconductivity on the surface, and then depending on their relative phase, you get topological superconductor or you get trivial. So if the 2 phases are the same, it's trivial. If the 2 phases are opposite, you get topological. But then the advantage is now we can make use of our understanding to this matter. This is the insulator. We understand the topological field theory, which is the direct generalization of the quantum Hall case in 4 plus 1D. You have this Chen term, and you apply it to the bulk. So now you ask, okay, what happens if I introduce superconductivity on the surface of this material with the Chen term? So what happens is you can basically reduce all the effect of superconducting phase fluctuation to this gauge field in the bulk, right? Because you can always do a gauge transformation and rotate all the phase on the surface to constant, and then as a consequence, you generate this gauge vector potential in the bulk. So then you just put that into your Chen theory, you're done, and then you get a topological field theory, which now you can write in the 3 plus 1D. So this was the work that we did. I did in collaboration with Xiao-Liang and Ed Wheaton. So we basically applied this kind of what is called Axiom field theory to this condensed matter system. So what you have is, it looks almost the same as the topological insulator case, but the meaning is very different. In topological insulator, this theta in front of the FYGF, in front of this term is just E dot B, and the coefficient in front of this in topological insulator is just a constant. It's like an order parameter. It's 0 or pi depending on whether it's topological. Here, the important thing is this is part of your system dynamics. This is a superconducting phase. It's the superconducting phase of one Fermi surface and the other, and the difference of them comes here. And then, of course, this superconducting phase will couple to the gauge field in the ordinary Ginzburg-Landau way. Okay, so naively, you would say in superconductor there is no electromagnetic field, so why do I bother to write this down? So that's true if you don't have any vortex. Then there is no electromagnetic field, there is no effect. But you can have electromagnetic field in the system when you have vertices, right? So for each vertex line, there is actually a flux line following it. There is a magnetic flux. So to get this non-trivial contribution of this term, which is E dot B, you need also an electric field. But you know that when you move the flux, you get an electric field, right? So what happens is you can take 2 vertices, one horizontal, one vertical, and then when you move this horizontal one, you actually generate an electric field this way. And then this electric field is parallel to the magnetic field of the other vertex. So consequently, what happens is whenever you have 2 vertex lines crossing, there is a non-trivial contribution of that topological term, which tells you this material is different from ordinary superconductor. So you can translate that into a very concrete statement. The concrete statement is you consider 2 vertices like this, crossing 2 other vertices of the left. If you have vertices of both left and right, then they will cancel each other. So you have 2 vertices of the crossing 2 vertices of the right, of the left. Sorry, crossing until here. And what happened during this crossing? There are 4 crossings between these 2 pairs. 4 crossings gives you this level crossing. When you look at the electron states, there is this level crossing which says, say this system has a ground state with even number of fermions, and this state actually has a ground state with odd number of fermions. That's it. Right? So this is an anomaly. It's actually a remnant. It's actually a residual effect of the anomaly you have in these wild fermions. So when you have superconductivity, most of the anomalies are gone, but there is a Z2 part left, which is like this. And you can also realize these vertices by introducing some S-wave superconductor on top of the P-wave superconductor. So I'm explaining this because it's non-trivial to realize this vortex of theta left without right. It's like any superconductor with different Fermi surfaces. Then there is a Josephson coupling between the different Fermi surfaces. Right? You never have a vortex of one without the other. But actually, on the surface of a superconductor, you can realize this vortex of only one Fermi surface without the other. And that's because this relative phase has changed across the boundary. So this is saying that you can actually realize this proposal in the system if you have this topological superconductor. So in the last maybe 5 minutes, I will talk about some more strongly correlated materials. So basically, so far what I talk about is this topological field theory gives you possibilities that can be realized in a given system. So it doesn't matter whether it's interacting. But so far the examples I talk about are those which may have interaction, but it doesn't have to. So there are richer physics in the strongly correlated systems which cannot be realized in this weakly interacting system. So this includes the fractional topological insulators. Actually, I should also add the reference of Andre and Xiao-Liang here. They first proposed this in 2D, and these are 3D proposals. So there are these fractional topological insulators, and there is also something like symmetry protected topological states, which are more like the TI in the sense that if you don't have symmetry, then they are trivial. But when you have symmetry, then you have non-trivial classification. So now in the following, I will give an example of this topological field theory approach to strongly correlated states, which is actually going back to the earliest topological states. That's the chiral 2D 2+1 topological order state, which basically means fractional quantum Hall. Okay, so you have these fractional quantum Hall states, and we know you can probe them by electromagnetic field. They have some ground state degeneracy, fractional particles, edge states, and you can probe them by electromagnetic field, but that's not enough. That just tells you Hall conductance. It doesn't tell you other things. So you may have different states for the same Hall conductance. So then that's why it was proposed that you can use the gravitational response to probe the system. So what does gravitational response mean? Like actually, when I talked to experimental colleague about gravitational response, he said, "Do you mean I just take your sample and throw it on the ground?" No, I don't mean that. But so what it means is basically you consider putting your system on a curved manifold and ask what happens. So this was proposed a long time ago, but actually it doesn't seem to be very clear what is the relation between this topological term and the physical consequences in the system. So that's what we recently figured out. We actually haven't finished writing the paper. So this is about how we really understand the consequence of this term and in what sense it applies to this system. And I will talk about two consequences. One is, well, I will mainly talk about one consequence. So the one consequence is you put your system on annulus geometry, but it actually has a cone. But now you change the cone angle. You gradually go from cylinder to, say, an annulus. This may be a plane, but it may also be an annulus with a hole in the center. Okay, so you ask, okay, what happened in this procedure? You ask, and then you take this topological term, and then you find out that what this topological term tells you is there is a pumping of angular momentum. So it tells, I mean, the angular momentum of the whole system must be conserved, but there is a flow of there is a density of angular momentum which goes from one edge to the other. That's exactly like quantum Hall case where you thread a flux and you pump charge. So that sounds straightforward, but we would like to verify that. We would like to take some system like P plus IV superconductor and really calculate this and show that that's true. We studied this using a method called momentum polarization, which we proposed in these two works. Actually, this is Zhang, E. Zhang, not A. Sorry. So basically, what this method do is you just take your wave function, twist it in some discrete way, and then calculate the overlap with the original wave function. And this allows you to measure the angular momentum carried by this edge without measuring the other. You just take this thing, twist it, measure the Barry space. And then using this method, we calculate in this work of Roger Mon and Max Zaletel and me, we calculate this angular momentum pumping when you tune the cone angle. And you see that it exactly agrees with this prediction of this topological term. So that directly verifies that, that indeed this topological term applies to the system. But there is another important information, which says if you take a space-time version of this, if you want to make this cone, but you make this angle direction actually time, then naively, if you follow this logic, naively this topological term will tell you that the heat current on the edge will depend on the gradient of temperature, because the gradient of temperature is like a cone angle, like the time is a radius in the temperature is like a radius in the time direction. So when you change temperature, there is a gradient, and then naively this term will tell you there is a heat current depending on cone angle. But actually, this doesn't happen. So it's another important information in this work is it shows there is indeed a symmetry between space and time in this system. So when you so there is no Laplacian argument like this in space-time. So you cannot have a heat current flowing through the bulk. And this actually can be understood by saying that the speed of light effectively is 0 in this system. So if you take that topological term, take speed of light to be 0, then that agrees with the results. Okay, so that's all I want to say. And in summary, this topological field theory is useful because it tells you all the possibilities without going into details. And there is a lot of open questions because so far the study is still sort of a case by case when you go away from these topological insulators. Thank you. It doesn't tell you it's a fermion, but actually there is something in the topological field theory will require that this cannot be a boson. So say there was this bosonic TI studied recently by Matthew Fisher et al. So if you try to use this logic in the boson series, write down the E dot B theory, you will find that actually theta equal to 2 pi is still non-trivial and 4 pi is trivial. So depending on whether you allow fermions to be a local degree of freedom in the system, you actually get different quantization. So in that sense, well, another way to say this is these topological theories give you anomalies on the boundary, and some anomalies can only be carried by fermions. So in that sense, you know it indirectly that there must be fermions. Yeah. Sorry? Depends on the system. In the 3+1 dimensional topological insulator, Maxwell is actually marginal. Maxwell is marginal. So that's actually one key difference. That's a very good question. So that's one key difference from the quantum Hall case. So quantum Hall case, the Chen-Simons term is the most relevant. You don't need to care about anything else, and that's why you can just do transport and measure quantized Hall conductance. In the 3+1, there is this theta term which is quantized, but there is Maxwell term which is as important as it. So when you measure this Faraday rotation angle, this rotation angle of the light, it doesn't directly just tell you this quantized number. It depends on dielectric constant and these things. You have to subtract them in some way. Yeah.
The response you calculated in the end, was that the transverse thermoelectric effect essentially? The response to the gravitational?
The gravitational.
The angular momentum dependent.
Sorry, the question was whether it's a.
Is it the transverse thermoelectric effect? Angular momentum change is a function of changing.
Yeah, it's like thermoelectric. If you think thermoelectric as a response to space-time curvature, this is a response to spatial curvature. So in that sense, maybe I don't know if it's called transverse, but.
The question is, can you measure it? How do you measure it in the lab?
Is that the question?
No, if it's alpha XY, it's something we can measure in the lab. I was asking whether it's connected to alpha XY.
No, the point here is these two are different. So this angular momentum pumping is something that can really happen in the bulk. So you have as annulus, you can really pump angular momentum from one edge to the other. Thermal Hall, you can have different thermal currents on the edge, and then they give you a thermal Hall, but you don't really have heat current flowing from one edge to the other. There's nothing flowing in the bulk. There's never anything flowing in the bulk. So that's actually different from the. Yeah, these two things are independent. Right? Because if you analyze this, you see one involves speed of light, one doesn't.
So
That's right. Yeah, that's a very good question. The short answer is I don't know. I would assume it depends on this, this like when you have 16 Majorana fermions on this vertex line, then there are some other ways to get it.
But my question is more to the point. So when you do modular invariance of things on the edge, somehow even though you do modular invariance for space theory, you get the correct dimension for interacting theory. Why doesn't this predict the correct dimension?
The correct dimension.
Well, so for example, if I do to prove that with interactions some Z classification goes into CA, right? I would impose modularity on the theory to show that the edge is not modular on the partition functions. Okay, but I would still do it with 3 fermions.
Yeah.
I would just take my partition function and project it into Sackler. I still do it with 3 fermions, but then I get the right dimension. Even though my calculation of modularity is done with 3 fermions, I would get the correct dimension that we get for interacting fermions.
Right.
So why? I mean, that's just.
I think it's because I think you can basically think this this interacting fermionic topological superconductor as maybe a non-interacting topological superconductor with fermions superposing some boson state. I mean, no, this doesn't have to be always true, but you can. But this is one possibility. You can have some boson state on top of this fermion state, and the boson state can give you something that cancels the fermion. And then what the boson can give you is well, I think what the boson can give you determines this periodicity. And the problem is we don't have anything like free fermion in boson system, which is free and gives you the right dimension. There's some in 2D. There's some transaminase theory to give you this. Not a bosonization. It's just I think the free fermion case is particular. It's because there is a free fermion which gives you this topological state with this edge state. For boson, you need the interaction.
If I understand it correctly, topological term injection doesn't contain metric tensor. So how does it feel what kind of surface?
Yeah, that's a very good question. So there are different meanings of topological terms. So when so there are terms like FYGF, which is just doesn't depend on the metric, but there is this gravitational term which explicitly involves the metric, but the metric is itself a variable, right? So that's another way to get a topological term. That in that sense, like all the gravity theories are topological because your background is background independent because the background is being integrated out. So in that sense, here this omega is the spin connection of the manifold. Thank you.